Okay, so hi, I am Maria-Nicoleta. Can you hear me? Well, okay. And I will talk about a version of the no-return sampler, which also works for the non-parametric settings. And this is a joint work with Lukong, Staton, and Matthijs Vákár. So first, I will briefly review Hamiltonian Monte Carlo, then two of its variants, which are the non-parametric Hamiltonian Monte Carlo and the no-return sampler. And then I will talk a bit about our contribution, which is the non-parametric no-return sampler, a hybrid between NUTS and NP-HMC. So for a long time now, there has been a dream to develop general-purpose inference algorithms that work seamlessly for universal PPLs. This is especially challenging for non-parametric programs where the number of parameters is unknown or bounded. So for example, take the clustering task where you don't know how many clusters you're going to have in advance. And I think Owen already gave some motivation for non-parametric statistics. So yeah, this is very challenging. And our focus is on Markov chain Monte Carlo methods, which estimate complex probability distributions by generating a sequence of samples through a Markov chain. And these distributions are usually defined on an infinite sample space. So our algorithm, non-parametric NUTS, is going to bring together two very different axes of development in probabilistic programming. So on one hand, NUTS is at the heart of the standard probabilistic programming language, and it works out of the box without needing to be tuned, unlike HMC. And NUTS has played a very important role in the large scale of use of complex Bayesian statistics across multiple sciences, and yeah, it's quite popular. However, NUTS is not designed to work in the non-parametric settings. On the other hand, NP-HMC makes it possible to use Hamiltonian Monte Carlo in the non-parametric setting by dynamically extending the traces when it is needed. So our aim is to build on that and to achieve non-parametric NUTS, which is a version of NUTS, which can be applied also on non-parametric models. So the goal is to sample from a distribution with density D, and we can view Hamiltonian Monte Carlo as an instance of Metropolis Hastings. So that means that we propose a sample and then we accept and return it with some probability given by an acceptance ratio. This acceptance ratio is very important, and it's specifically designed to preserve detail balance, which is important for proving convergence to the target distribution. So unlike other algorithms like random walk Metropolis or Gibbs sampling, HMC differs by using gradient information about the log target density, and this makes it converge much faster to the target distribution. And especially for high-dimensional spaces, like other methods might take a reasonable amount of time, but HMC still works on them. That's nice. I will try to give some intuition of how HMC works. So we want to sample from the distribution D. Now imagine that we have a surface that describes the function minus log of D. And if we want to get samples from D, that means that we want most of our samples to be in the value areas. And yeah, if this surface is frictionless and we put a pack on it, then the pack will mostly go at the bottom of the valleys, and that's okay most of the time. However, once in a while, we also want to get samples from the sides of the hills or the top of the hills. And to do that, we can just get some impulse with some momentum P, which is going to be random, to the pack. So now the pack can also get to the top of the hills or even change valleys. And yeah, P is an extra random variable, and it's normally distributed. So now we can propose our next draw Q by going for some time t with momentum p and see where the pack ends up, in what position it ends up. Okay, so to do that, we can use Hamiltonian dynamics, and the system is described by the Hamiltonian H, which is the sum of the kinetic and the potential energy. So now we'll have states formed of position Q and momentum P, and at the end we will have draws from this distribution mu. So since we can see that Q and P are independent, we can just ignore the draws for the momentum P, and then our draws for Q they're going to be from the target density D. So that's what we want. Oh, it's falling. Is it better?
I think so.
Okay. So now the values for Q and P after some time t can be computed by solving these differential equations. However, we cannot do that exactly in practice. So we will approximate them by discretizing time. And one common approach of doing this is by using the leapfrog integrator, which simulates L steps of small size epsilon. And epsilon and L need to be user specified. So this is how one iteration of HMC looks. So we start with the position Q, then we sample the momentum, P. Then we apply the leapfrog integrator on it, and to account for the error introduced by the approximation for the simulation, we also have to have an accept or reject state. However, if we can control the simulation error, then the acceptance ratio is going to be very high. And that's nice because we can, in one iteration, we can end up further away from where we started and still have high acceptance, which is preferable compared to, for example, random walk metropolis, where the further away we go from the initial state, the lower the acceptance probability is going to be. So to sum it up, HMC uses Hamiltonian dynamics to propose the next step, and it's quite efficient, even for high-dimensional spaces. However, it's very sensitive to the number of steps that we have, L, and the step size, epsilon. So, for example, if the number of steps L is too large, then we might waste computational power by exploring the same area multiple times in one trajectory. On the other hand, if L is too small, we might get stuck in some local minima area, and the gradient information is going to be less influential, so it's going to result in more of a random walk behavior. And this is why NUTS wants to adaptively set the length of the trajectory at each iteration. So the idea behind NUTS is to choose L such that we stop the simulation when we start to head back, so in the sense of like we start to make a U-turn. And to do this while also preserving the balance, it's a bit more subtle, and it involves iteratively simulating either forwards or backwards in time for a double amount of time until we see that we made a U-turn. At the end, we'll have this trajectory of states, and we'll sample the next state according to the weights of the states. So for example, here, we start with one state, and then we choose the forward direction, and we go one simulation steps forward in the direction of the momentum. And then we choose the backward direction, and we go two simulation steps in the opposite direction of the momentum. So those are the yellow circles. And so on until we stumble upon a U-turn. And notice that we can view the trajectory as the leaves of a perfect binary tree, which is quite important. So one property that this final tree has is that we can construct this starting from any of the states in the tree. However, you need the doubling directions to be accordingly for each state. And this is important for detail balance. So as I mentioned, we stop when a U-turn was made. So how we can check this for a state Q and P, if we move with momentum P away from Q, we start to get closer to another position in the trajectory Q prime. So yeah, we just have to check this inequality. So NUTS is very clever about how the construction of the tree is made, and not all the nodes need to be stored at the same time. So that means that we also don't compare every pair of states in the trajectory to see if they made a U-turn. Only the leftmost and rightmost leaves of the tree are compared. So we saw that NUTS is a performance variation of HMC, which avoids manual tuning by setting the number of steps dynamically, that is using the doubling procedure and the no U-turn criterion. And moreover, this is done efficiently while recursively constructing the tree which contains the explored states. So we talked about HMC and NUTS. Now we'll see how these algorithms can also be applied on nonparametric programs. So for a probabilistic program, a trace is a sequence of sample values during one execution. And different runs of a probabilistic program might result in different traces of different length. And this can happen, for example, if you have stochastic branching and for loops or recursion. And since we don't know we might not know an upper bound on the length of the traces, This is what our target density is going to look now. So it's going to be defined on the union of R to the n. So now if we try to apply HMC on such a probabilistic program, during the computation of the leapfrog integrator, we'll go through multiple positions Q, because we'll make L steps, so we'll have L positions. But for some of those, it might happen that the position Q is not long enough. What that means is that if we run the probabilistic program on it, the values in the trace Q are going to use as seeds for the sample statements in the program, but they are not going to be enough, and the program will need more seeds. So in other words, we'll have that any prefix of Q is not going to be in the support of W, and this is not what we want. So we want to extend Q so that Q ends up in the support of W. And NP-HMC does that by running the probability program P on Q, and then sampling the extra dimensions using the sample constructs that are encountered in the program. So at the end, we'll have that Q is in the support of W, and then we'll have to extend P accordingly to match the dimension of Q. And then we also have to extend the initial state, Q0 and P0, because it's going to be needed in the computation of the acceptance ratio. So NP-HMC deals with not long enough traces by extending it dynamically during the leapfrog integrator. And the acceptance ratio has to be carefully computed. So there are multiple ways of performing extensions, and one of our contributions includes some acceptance ratio together with a correctness proof for some of these ways of performing extensions. Okay. Yeah, so now we are going to talk about our contributions, which is NP-NUTS. And in order to combine the ideas of NUTS and NP-HMC, multiple things have to be taken into considerations. Of course, during the doubling procedure, we might need to extend the traces and also extend the other states accordingly. And then in order to sample from the next state from the constructed tree, we will need to know the weights of each state relative to each other in the tree. And this becomes tricky because the weight of the state depends on the probability of constructing the tree starting from that state. And moreover, that depends on the likelihood of the extensions that are made during the construction. And the fact that for each state we have different doubling directions that we need to take in order to make the tree makes this even more complicated. So a naive approach to this would be to just simulate the construction of the tree for every state and compute its weight. But of course, it would take way too much time. So we want to be able to construct the tree once and also not store all the nodes, just like NUTS does. So fortunately, we can do this by recursively combining extension likelihoods in order to compute the relative weights of the trees, of the subtrees. Another thing is that the no-return criterion must be modified. And this criterion should not depend on the extensions that are made, which are not relevant to a state. So as I said before, if you extend the state, you also need to extend the other states in the trajectory. But yeah, for some states, those are kind of irrelevant. So they shouldn't be included in the stopping criterion. And this is one possible way of doing it, but there are multiple others, and we're also interested in exploring them. So we hope that NP-NUTS will be effective for models with a large number of continuous parameters, as well as some of non-parametric features. And we are also interested in devising a version of NP-NUTS using laziness. So for example, implementing it in lazy people. And we also want to explore more versions of NP-NUTS. These include different stopping conditions, and these can also depend, for example, on the number of dimension changes that we made, or just how many times we extend the trajectory when we make the trajectory. So yeah, that's about it. Thank you very much, and I'm happy to talk about it at the poster session.
Thank you, Maria. We have time for one or two questions, I think.
Thanks a lot for the talk. So one quick question, I'm not sure I followed, but when you add these extensions, is it for just one step and then you restart for the next one, starting with the original dimension of your problem? Or do you keep the maximal dimensions that you ended up with so far?
So we keep the maximal dimensions. Maybe at the next, sorry, you mean from one iteration to another?
Yeah.
Oh, no, we can just get rid of them if they are not relevant. So it's kind of like marginalizing them out since they don't affect the result or the weight of the program.
Right, so the gradient that you compute at each step does not have the same dimension.
So the gradient does not depend on the kind of extra extensions, like the irrelevant ones, if that's what you were asking about.
Okay.